Let's wait for all the internet things to connect to each other. Oh, we're on. Fish on. Boom, boom, boom. I'll get this over here. Wonderful. Hello everyone. Today we are going to be replicating some time series papers and researching time series materials. I'm just going to, before we get started though, I'm going to just share this out on Twitter, sorry. Twitch.tv/Mr. D Burke. Can I see myself? If you're joining, that sounds good enough for me. So let's go into here. Twitter. If you're joining, you know the drill. Oh, ETA 2022, Jeremy Howard. I need to save that to bookmarks. Beautiful. Oh, Jeremy Howard. So this is the danger of Twitter, right? You jump on Twitter.
And welcome to the everybody, and welcome to the.
Need to save that. Okay. Now, boom. Going live on Twitch. Doing time series or time series forecasting. No, let's go, what could we say? Researching time series forecasting with deep learning. No, researching deep learning methods for time series forecasting. Plus plenty of TensorFlow code. Come and say hi. All right. That should be good. Going live on Twitch. Beautiful. Tweet that out. Okay. Now, we actually need Google Chrome. So, okay. Let's see what we got on here. Oh, I'm going to also share this out on Discord. We'll get started in a second, all right? We're just getting warmed up. If you're joining, please let me know if you can hear me in the chat. That would be very helpful. So I'm just going to go machine learning data science. Going live on Twitch, streaming time series with TensorFlow, research, coding. Hands-on ML. Second. All right. So here we go. So here's what we're doing. So I just released this course a few days ago. Oh, well, in the last couple of months. We've worked on this before. But long story short, we need to release the final modules coming out. I've recorded videos for 08 and 09, so NLP. But time series fundamentals I'm still making the materials for. So that's what we're going to be doing today, is mostly researching materials for this and also coding them up. So let's jump into a Colab research notebook. So over the past few weeks, I've been looking into just time series forecasting in general. So it's a little bit of the funny thing about time series is that, let me define that. Time series equals, which one do I want? I'm gonna go new notebook. Time series equals predicting, or no, this is better. Using data from the past to try and predict the future. I'm going to put this as a dot point. Beware though, many forecasting methods are overblown in their ability to predict. It's basically like fortune telling. So that's a big caveat. So let's write in here, what could we call this? Time series with TensorFlow research. Okay. So there's a paper I found the other day, which I'd like to try and replicate. There's also a forecasting, so there's a big competition. This is gonna be pretty erratic, this stream. So M competitions is, how would you say? How do you pronounce this? Makridakis, I'm probably pronouncing that terribly, but that's my Australian accent coming out. So Makridakis competitions are also known as M competitions. They are a series of open competitions organized and led by forecasting researcher Spiros Makridakis and intended to evaluate and compare the accuracy of different forecasting methods. So I believe there's been 5 M competitions so far. 1, 2, 3, 4, 5. And fun fact here, that the winner of the number 4 competition was someone from Uber. Now, if you look at Uber, forecasting is a big part of their business. Why? Karturo, use LSTM for forecasting. We will see. We will see. So LSTM is definitely one option for forecasting, but there's a method that I want to try and reproduce, and I've got a little bit of a blocked nose, so apologies if I have to blow it during the stream. I know it's not very polite, but if you want me to be able to breathe, I need to blow my nose. So, okay, there's a paper I'd like to replicate, but you can read this. Uber forecasting. If you imagine what do you have to do, you have to forecast how many cars do you need on the road. Look at this. This is Uber's demand in San Francisco. So you need to be able to understand like what you need. You also need, what kind of hardware do you need? Such as in compute power and all that sort of stuff, marketing. How do your advertisements go? Are they returning what they should be returning? So of course, forecasting is challenging, yada, yada, yada. But the main thing I want to look at is, if we look at the Makridakis competitions, is that what it's called? Makridakis? Yeah, M competitions. There's an algorithm called NBeats. NBeats algorithm. So this is neural basis expansion analysis for interpretable time series forecasting. And so we focus on solving the univariate time series point forecasting problem using deep learning. We propose a deep neural architecture on backward and forward residual links on a very deep stack of fully connected layers. The architecture has a number of desirable properties, yada, yada, yada. We demonstrate state-of-the-art performance for 2 configurations of NBeats for the data sets, improving the forecast accuracy by 11% over statistical benchmark and 3% over last year's winner of the M4 competition, right? So this is a pretty good algorithm for univariate time series point forecasting. So if we look at this, the M4 competition was someone from Uber. Uber do a lot of forecasting, so this guy's probably pretty good at forecasting. But this paper, NBeats, beats it. So I'd like to practice. I'd like to re-implement this algorithm. What does the time series module need to cover? So there's going to be a fair few things that we want to cover. Try to use the transformer. That could be an option as well. I wonder if transformers have been used for time series. Transformers for time series. Oh, here we go. Deep transformer models for time series. How does it go? Attention is all you need for stock forecasting. Here we go. What does it do? We present a new approach for time series forecasting. Moreover, it is a generic framework and can be applied to univariate and multivariate time series data. Are favorably comparable to the state of the art. Okay. Transformer model. LSTM. Where's the results? Favorably comparable. Transformer. Okay. Here we go. Okay, so we've got a fairly low RMSE. All right. So that is cool, transformers for time series. But I'm going to focus on this one and beats, just because I saw it the other day and it sparked my interest. And I think it's only using fully connected layers, so that'll be fun to reproduce. There we go. It's by Joshua Bengio. I'm going to write down here. Let's see. We want this, replicating that. So what needs to be covered in a Mark, what's going on, my friend? Good to see you. You know, I've been down a rabbit hole of your work lately, and it's absolutely outstanding. So let's see what we need to do for time series. I've never really worked with much time series data, but of course we need to get data, format data. Things you need to do in time series is like remove seasonality. So if your data has one sample per month and it has a seasonality of 12. So seasonality is, we'll get into that in a second, but I've got some notes here of what I've collected. So detrend the data, turn it into, so what you're doing with time series forecasting is you're basically turning it into a supervised learning problem. So you're using some sort of section of data from the past, so like last month's Bitcoin price to predict tomorrow's Bitcoin price. But we're probably going to see in a later stream how terrible that actually is. Windowing, this is just an exploration into, then obviously you get a baseline, important. Actually, I'm saying obviously, I need to reuse my language because you might not know that that's obvious. But important for ML problems, start with a simple model. So a good baseline in time series, can you see all this, or is my face in the way? Oh, my face is in the way. And let me move me up here. There we go. You don't actually need to see me, but why not? Get a baseline. So a really naive baseline in time series equals predict the last time step as the next step. So you'll actually find that this is actually really hard to beat as a baseline, especially with like deep models. So that's actually a really good baseline. So once we've got a baseline, what do we need to do? Build more models to beat baseline. Okay, so once we've got a baseline, there is also different methods to evaluate time series models. So of course you've got like MAE, MSE, mean absolute error, and mean square error. Then there's mean absolute percent error. Percent error. Is that what it's called? MAPE? Mean absolute percent error. Yep. What else do we want? Time series. There is also univariate versus multivariate time series problems. So univariate equals you have one variable, such as price of Bitcoin over time. So if we look at this, Bitcoin price, if we wanted just the univariate, a univariate time series, we could go the price of Bitcoin over the last, whatever that is, 10 years. And then we were just trying to predict the next price based off the previous price. But multivariate equals you have more than one variable, such as a computer network system with many inputs, like room temperature, number of users on the network, etc. And you're trying to measure, or you're trying to forecast how many. If you're Google and you're building a service like Google Colab, and you want to, that's probably a good idea. And you want to forecast like how much compute you need to dedicate towards Colab instances for a particular day, you could use a multivariate time series model to predict that. Now, there's also the thing about being able to quantify our confidence. So I'm going to show you an article that I think if you're interested in forecasting, you should definitely read. It's probably full of terms that you're not, if you're new to forecasting, it's probably a little bit technical. So I'll show you some resources that are great for getting up to scratch and what you need to understand for forecasting. But is as important as being able to make a forecast. So this is also referred to as uncertainty. You might also hear it as confidence interval. You might also hear it as prediction interval, etc., etc. So if we look at this, let's just go prediction intervals, time series. Yeah, there we go. Time series. Why? Like, Google Images is a great service, but is it just me, or does that it usually produces like crap results? Like some of the images are just all over the place. Like Google search is great, but I think they've canned images. I think they can do a lot better with Google image search. So yeah, there you go. So this is a very important point. We're going to look into this in probably a later stream, actually. So if we look at this, Uber uncertainty. This is a great article. Engineering uncertainty estimation for neural networks in time series prediction at Uber. So again, we've said this at the start. Uber is forecasting is the majority of their business. So, or a big part of their business. But what they used is Bayesian neural networks, which is a fancy way of saying they implemented Monte Carlo dropout. If we go here, Monte Carlo dropout. Right? So model uncertainty. And this is another thing with the machine learning world and whatnot, is that you're going to see a lot of symbols with the math, and I'm going to be straight up with you. I can't read those. There has to be a model somewhere, LaTeX to English. So it would take me a fair while to deconstruct this. So my brain is attuned to reading code and writing code rather than looking at math, which is a weakness in my capabilities. It's something I want to work on. But anyway, Monte Carlo dropout is, see look, if you read this, like for me, this is Monte Carlo dropout, right? But one way to do this, Monte Carlo dropout, which is basically use dropout at inference, and run multiple simulations. So I really wish someone would just say that in the paper, rather than, I mean, this is important, I guess, if you're in academia, to show them that you can write this fancy stuff. But it's like, if we go to Colab, you can, in TensorFlow, dropout is like layers.dropout, 50% dropout, training equals true. That is literally Monte Carlo dropout, and then you write a for loop. For I in range 100, you do model.predict x, but when your model is predicting, dropout has training turned on, so it uses training, it turns dropout on an inference. That is Monte Carlo dropout. And the reason why it does that is, that's one way of simulating, I can't pronounce this correctly, but it's, oh no, I've got a better way to do it. There is two types of uncertainty. So I want to teach you the intuition, or at least talk myself through it, because by the way, I'm still learning this as well. So don't take everything I say here with a grain of salt. I'm still learning this as well. The two types of uncertainty is coconut uncertainty, right? Which is, you're sitting on a beach and you get hit on the head by a coconut. And I'd argue that that's probably even not a great analogy. If you've read a book called Fooled by Randomness, there's like different types of randomness. Fooled by Randomness by Nassim Taleb. I'm probably butchering everything how he describes it. So one type is coconut uncertainty. You're sitting on a beach, you're not expecting to get hit by a coconut on the head. However, I would also argue that if you are sitting on a beach, you kind of have that expectation. But the coconut uncertainty is kind of like a black swan. So like something you can't predict. Whereas subway uncertainty is, and we're going to loop all this back and how this works into forecasting somehow, I hope. This is not very structured stream, hence why it's live. Subway uncertainty is, your train should appear at 5 p.m, but it shows up 1 to 2 mins either side. And so going back to Uber's, they got a good graphic here of their Bayesian. Yeah, so see, hopefully you can see this, because even it's a bit pixelated on my screen, but see like the gray lines? So their prediction is the blue line, okay? But what the gray lines here is saying, okay, this is our prediction, which is a point estimate. A point estimate is like, it's going to be this value. Whereas the uncertainty that they're engineering into this with Monte Carlo dropout is this gray section. So even though they're saying, like, let's make an arbitrary value, this is 100, right? Like, so this point in time is 100, making that up. But they're saying that the model is going, hey, you know what? We're predicting 100 as the actual value, but we've predicted as low as 50 and as high as 150. So there's that range of values that it's predicted. And so being able to quantify this confidence in a forecast is as important as being able to make the forecast. So if you're making a point estimate of 100, but you're also saying that, hey, we're saying that it can be 100, but it can also be 150 and it can also be 50. That's a lot different than saying it's just going to be 100. And so this is the equivalent of subway uncertainty, which is, the formal word for it is aleatory uncertainty. Aleatory. I'm probably saying that wrong again. And this is epistemic uncertainty. Now, the intuition here is, again, I want to build this up from an intuition standpoint rather than just throwing you mathematical formulas. The coconut uncertainty is you're sitting on a beach and you get hit by a head with a coconut is an epistemic uncertainty. Now, we can sort of engineer subway uncertainty by using methods like Monte Carlo dropout. So simulating, have a neural network, train your neural network with dropout, and then run dropout at inference, do 100 different trials, and you'll notice that because dropout is going to drop out random neurons as you're training it, it's going to produce, say, 100 different predictions if we ran this code, dropout on it training time. So you would have 100 different prediction probabilities for a single point. And then what you could do to measure the subway uncertainty would be to take the variance of those 100 different predictions. And so you would get some sort of range of where your predictions lie, which is where they've created this graphic here. You get that range. So rather than just being a single point, when you make one prediction, because you're making 100, you get the variance of where your model's predictions go to. However, epistemic uncertainty, you can't, it's almost impossible to estimate. Because this is, you basically have to reproduce the entire world to try and forecast that. But subway uncertainty, you all know this intuitively. When you go to a train station and your train is supposed to get there at 5 p.m., you know that it's probably, if it shows up 1 to 2 minutes either side, well, that's a normal event. But say your train was hit by a meteorite, you can't really engineer that into a model of predicting when your train was going to appear. Because that's just something so outlandish that it can't be embedded into your model. So this is epistemic uncertainty is usually model related. So uncertainty equals model related. Your model doesn't reinvent the whole world. You also know this firsthand as well with weather predictions. So imagine like how often are weather predictions right? Of all the sensors and all the data that they have, one of the best weather predictors is to just look outside, right? So my weather app on my phone could say that it's sunny in 3 hours, but if I look outside and see clouds everywhere, well, what am I going to trust? So that's another thing. And then, so this is aleatory uncertainty equals data uncertainty. Yeah, Mark, you're right. The Taleb's, I'm currently going through, I've like bounced back and forth. I've got the Inserto series on my bookshelf. I'm kind of bouncing in and out of them for the second time. Yeah, Mark's correct. So this is weather equals predict sunny every day in San Diego equals good model. All right, now let's, where were we? Carturo says predict COVID, is it univariate or multivariate? So Carturo, I'll show you an example. So number of COVID cases worldwide. And let me get back to the article I wanted to show you. So why you should pay attention to Nate Silver versus Nassim Taleb. This is a great article which discusses these type of uncertainties. Mark, you'd actually really like this article if you haven't already seen it. So it's 3 years old, but I'm going to put this on here. But Taleb's having a go at Nate Silver, who makes a prediction website, or used to make a prediction website on politics. And this gentleman, Isaac Faber, who's, I believe, the chief AI scientist in the US military. So he knows his stuff, or you'd hope so. But what this is basically saying is, yeah, a forecaster should be held responsible for both aleatory and epistemic uncertainty. So the uncertainties that we discussed, it's saying this article is Taleb's argument is saying that these are the two lines. So again, Nate Silver made a website that predicts politic outcomes. So if we imagine politic outcomes, that is a severely multivariate problem, open system. So let me write down here. Politic outcomes equals open system, many different variables. If you're going to predict or be making forecasts, you should be responsible for, first of all, uncertainties and your predictions at every single time. So this is what Taleb is saying that you should be accounted for, and Silver thinks you should be judged by your last estimate. Make what you want of the article. I'm going to side with Taleb, partly because my cognitive bias is that I'm a fanboy. I've read his articles. I'm nowhere near as smart as any of these two gentlemen. However, just from experiments that I've run, it makes sense. It just makes sense. Think about how you think about the weather. The weather is an open system, many different variables, and how often is the forecast wrong? Okay? So this is where you see, like so this is a univariate problem. Katuro asks, predict COVID, is it univariate or multivariate? So Katuro, this is an example, COVID-19 cases around world. If we just wanted to predict off the simple count, I mean just the number, so this is my country, Australia, Queensland. So if all we wanted to do was predict tomorrow's cases based off the number of cases were today, that would be univariate. Whereas if we wanted to build a model that took into account, I don't know, everything, the number of people visiting shopping centers, the number of people on buses, the number of, like, just, that's why, like, models, like, just break down with COVID, because you're trying to forecast, you basically have to simulate the entire world to get an accurate prediction. So anyway, you see these models, they're just breaking down everywhere, which is why Taleb's focus, like Nassim's Taleb when COVID came out, was when you have such an incredibly unmodelable phenomena, you should take the most what's it said? You should panic the highest when the prediction outcomes are complete, like you can't predict what's going on. So you should stay inside, even if we don't know that these things work, right? So, okay, we've kind of done a big roundabout loop, but we now have an outline of what we need to do. We need to get data, we need to format the data, we need to get some sort of baseline, we need to investigate what sort of evaluation methods we have. We need to decide whether our data is univariate or multivariate, which is pretty quick, we can decide on that. And then when we make forecasts, instead of just making point forecasts, we need to be able to quantify what our confidence level is in forecasting that. And there's two types of uncertainty for that, which is coconut uncertainty and subway uncertainty. The formal names of each is epistemic uncertainty. So this is model related. In other words, your model doesn't take into account all of the parameters that go into some sort of system. Aleatory uncertainty is data uncertainty. Okay. And one method for estimating, or epistemic uncertainty is basically very hard to estimate. And then aleatory uncertainty can estimate with techniques like MC dropout. Okay, now let's go back to the paper. So there's an algorithm called NBeats. which is from Element AI, which is apparently really good on the M competitions. Let's go. Can we figure out what the M competitions are? Forecasting competitions, right? So let's figure out where this is. This is where I found this algorithm was. Okay, M4, M5. Let's go M5 competition results. M5 accuracy competition. Let's have a look at this paper. Do we have results? Far out, this is very long. So basically, the crux of this competition was we have 100,000 sets of forecasting data sets. Here we go. And we'll pay you to build the best forecasting model. Again, I'm still learning about this, so take everything I say with a grain of salt. Here we go, results. So what measure is this? So they measured accuracy in terms of metric. What is this? This is a very interesting loss function. Objective function for WR, what does it even stand for? Oh, they probably defined it in the paper, didn't they? I actually want this in another tab. What's it called? WRMSSE. Weighted RMSSE. What's this? Root mean square error equals weighted. Oh, so the number of data sets. Okay, so there's 42,000 data sets. Weighted root mean square. Let's just Google it again. Scaled. Okay. Root mean. Okay, so it's scaled in some parameter. Root mean squared error, but I'm guessing the extra S in this one is scaled. So weighted, let's write this down so we don't forget. Weighted RMSSE equals weighted root mean square scaled error. Maybe. I don't know. Let's get to results. I just want to show you where N beats was. First place. So I think the majority of submissions actually won with a light GBM algorithm. So deep learning may not even be the right thing to use. But since I'm currently deep in TensorFlow, I just want to practice replicating stuff. So here we go. First place, Yeonjun Im, the winner of the competition, a senior undergraduate student at South Korean. Yeah, used various LG light GBM models. So light GBM is Microsoft's version of a gradient boosting machine. Come in there, boom, light GBM. You can use that package. So this one actually won a stack of this. This is classic Kaggle 101. There's probably a meme for this. Kaggle 101 equals stack together ensembles of light GBM / XGBoost. Kaggle 101 is got tabular data, then stack together these. As we just saw, tabs are already exploding. But the second place is where I found this. This method, also based on an equally weighted combination of various LGBM models, was externally adjusted through multipliers according to forecasts produced by NBeats, right? NBeats, Deep Learning Neural Network for Time Series Forecasting, which is where we come into this, which is they beat the M4 competition. However, I think they get bested in the M5 competition. That's enough background of why we're using this algorithm. Let's try and reproduce it. I believe they have a GitHub on this, but I'm going to, because I want to practice my code, I want to try and reproduce it myself before looking at an example implementation. So this is it. It's a stack of fully connected layers. That's basically it, with skip connections. So if we break this down, you prepare your data in some format, you put it into a block. The block is a fully connected stack of 4 fully connected layers, and some of them, it outputs into 2 fully connected layers. One goes backwards, one goes forwards. You stack together multiple of these blocks with, again, skip connections. This is what this arrow is doing here. Skip connections was introduced with residual neural networks. Skip connections. In ResNet, you're jumping from, I want to really fix my speech with saying basically and obviously, because that's not considerate of if you've never heard of this. So if we have an input X, a skip connection is we also pass that X to the output of 2 certain layers. So this is a residual learning, a building block. So what they've done is they've taken this idea of skip connections from ResNet maybe and applied it here, and they create stacks, and then they combine more stacks, and eventually you get this massive neural network, and you start forecasting from there. What's the loss function? I don't know. Loss. Here we go. Losses is a set of loss functions that used to build on. Okay, so maybe it's an ensemble. We observed on the respective validation sets that for M4 and M3 mixing models, MAPE led to the best validation scores. So MAPE is what we discussed before, mean absolute percent error. Looking back, used a batch size of 1024. So this might be, okay. So again, another thing you need to keep in mind for time series is that neural networks tend to train on large amounts of data. But the price of Bitcoin is very good to as a univariate time series, because it's just, well, any stock price could be a univariate time series. Again, keep in mind, any type of model for stock predictions is basically like fortune telling. So this is just an example. It's because it's easily accessible data. Do not take the outputs of your LSTM model for Bitcoin prices as investment advice. But yeah, so even if we took from Bitcoin's inception 1 data point per day for the last 10 years, what does that only gives us 3,600 data points. And so as you're aware, neural networks take a lot of data. So ImageNet is like something, 1 million images or whatever it is, but the entire history of Bitcoin is only 3,650 steps. So let's find out what data set they used. I'm going to bring this over here. Mark actually has a great tweet on this. Shivans, what's going on, my friend? Renjaju says, what's my preferred way of writing ML code? When I'm hacking around, I write basically at the moment exclusive. I'm going to get rid of that ad that's flashing in my face. When I'm hacking around, I just write in Colab, basically. Like today, we're going to just be writing in Colab. But when I want to build something actually worthwhile, I do like scripting and all that sort of stuff. But let's go here. Want to replicate this. We need to get data, format data, build model, test model, play around with uncertainty. So this model doesn't actually have dropout in it, I don't think. So the reason why Uber used Monte Carlo dropout is because deep models typically have like dropout layers. So they only mentioned dropout once in the paper. We found that ensembling is much more powerful regularization technique than popular alternatives like dropout or L2 norm penalty. Okay, do they mention uncertainty in here? Uncertainty, no. Once again, we have an ML paper that just improves on one metric and doesn't talk about other things that are very important for time series data. Do they have a limitation section? Do they have a code section? Christ. What do they have? Now, this is where is the network? Here we go. Okay, let's find the data. Do they have a section that says what data we used? We test the proposed architecture on several well-known datasets, including M3, M4, and tourism competition datasets. Okay, so which dataset did it perform the best on? We'll get that dataset if it's public. My goodness. M4. Why read the whole paper when you can just hack around and search for it for 3 days? M4. Oh, come on, man. Okay. So the M4, okay, so all right, we might run into a problem here. They used lots, M4 dataset I believe is lots of datasets. So M4 average, 100,000. Is it easily accessible? M4 dataset access. Here we go. What's Kaggle got for me? Oh, Data Explorer, boom. All right, we might be on here, team. M4, 100,000. Tourism. So N beats is the algorithm. M4 average. Let's have a look. Let's actually read some of this. There we go, trend model, seasonality model, generic architecture. Now, the reason why I'm kind of interested in replicating this is because it uses just fully connected layers. And this is actually a recent, well, we saw this the other day, is MLP Mixer, which used good on him. Rakesh for replicating that real quick. Well, I suppose the whole thing is just MLPs, which is a fully MLP model for vision, which is competitive with state-of-the-art transformer models, but it requires a lot of scale, CNNs, yada, yada, yada. But this is all MLPs. So this is why I'm interested in replicating this, because that could be a trend going forward. Mark's tweet's actually really great on this. Same vibe Twitter. I was Googling that before. You should all go follow Mark, by the way. Mark puts out amazing things in the machine learning world. I'm a big fan of his work. But yeah, the year is 2030. Google, Microsoft, and OpenAI have merged. Preprint on archive acquired by GitHub. Fully connected neural networks is all you need. SOTA on all tasks. And then replies to his own tweet. MLP mixer coming out, an all MLP architecture for vision. Again, getting distracted by Twitter, but shout out to Mark. Go follow Mark. Let's find the actual data set. Yeah, look at this. So the best ranking models were ensembles of classical statistical techniques. So in time series or this type of data, ensemble is your model of choice. However, for the M4 competition, Simul, which was from Uber, remember Uber, forecasting is very important. There. Oh, the author, look at that. We're connecting the dots here, people. So the M4 competition was also the person who wrote the forecasting at Uber and introduction. That's awesome. There we go. So this gentleman, forecasting expert at Uber. Star work is ranked highly in international competitions. For example, he won the M4 forecasting competition. Lovely. And he used a hybrid model, a hybrid between neural residual attention dilated LSTM stack, so LSTMs with attention, and a classical Holtz-Winters statistical model, so an ensemble. Yeah. They say further argue that hybrid approaches and combinations of methods are the way forward for improving the forecasting accuracy and making forecasting more valuable. In this work, we aspire to challenge this conclusion by exploring the potential of pure deep learning architectures in TS forecasting. Wonderful. Summary of contributions, problem statement. To the best of our knowledge, this is the first work to empirically demonstrate that pure DL using no time series specific components outperforms well-established statistical methods on M3, M4, and tourism datasets. Yeah, so that is why I'm excited about this. If anyone knows of a deep learning approach that beats NBeats, please link it to me. I also know that I could look up on GitHub, the code has been implemented for this, but I want to practice doing it myself. Our architecture relies on a few key principles. Basic block. Okay, we've looked at the architecture. I just want to find the data set. That should be like a real specific thing at the start of the paper. It's like, here's the data we used. If it's proprietary, great. Don't give it to us. But just tell us, like, in plain English, what data set you used. Draw a colorful diagram like this of the data that you used. Draw a colorful diagram. Break it down for monkeys like me who want to use your work. Trend model, ensembling, pure ML, related work. On M4 dataset. Okay. All right, so the M4, let's read this info. What have we got about this? Paper describing the competition various benchmarks. The data is available on the MOFC. Shivan's Uber uses forecasting. So that's one example. A lot of businesses actually, so forecasting is the thing that like businesses use to, how do you say, MBA types at businesses, like kind of, they need to have meetings about something. So they need to go to the stats and data scientists and go, give me a forecast with a graph that goes up and to the right, so I can talk about something in a meeting. That's the type of people who use forecasting. But honestly, it is actually a challenging problem because if you read the Uber's use cases, like they make sense. Marketplace forecasting, hardware capacity planning, marketing. A great example is like Google Colab, right? So rather than Google having 10,000 machines sitting idle ready for Colab, it's like, okay, we know that not as many people are going to be wanting Google Colab machines at nighttime, so we're going to dial down those machines. But when we have people wanting resources, we're going to dial them up. So that's like a forecasting problem. Here we go. Download the trained dataset here. M5 dataset. I want M4. Wait, did they predict on every single... Are you kidding me? Am I being hoaxed here? Am I reading that the series were selected randomly from a database of 900,000 ones? So the M4 dataset was random. I need to read more into this. Oh, here we go. Train. All right, so I'm just going to import this from GitHub. Let's do that. Christ. Do I have to clone all of these? Dataset. Can you clone just a specific file from GitHub? Is my naive knowledge of GitHub revealing itself? Of Git? I just want the dataset folder. Who knows how to clone an individual folder from GitHub? Git clone .git. Is this going to work? Fatal. Did that just work? No. Who knows how to clone a single folder from a GitHub repo? I'm going to move myself back down here. How to clone single folder from GitHub. No, that's not possible. Stack Overflow to the rescue. If I'm missing something, link me. Otherwise, I just want this dataset folder. How big is this going to blow up Colab storage? I need .git, don't I? No, maybe not. You mean the link here? I need the full directory. M4 methods. This folder, you mean? Yeah. The file is challenging. Oh, it's only 1.5 gigabytes. That's not too bad. ls dataset. There we go. Dataset. Boom. Now, what's inside train? Okay, let's have a look. It might be the same data for. I hope this wasn't just randomly generated, and that's what they've built this model on. Randomly generated data. df equals pd read csv. Let's visualize it with pandas. We need to know what data we're working with. Does TensorFlow have MAPE? It does. Boom. Okay. What is this? 5 rows. Don't tell me. So they're 10,000 data points? M4 competition paper. So their model went across all of these. All right, so that's the daily. Why does no one have a schema? Why is this columnar? Columnar. start a new benchmark. We could put their benchmark on here. What does the weekly data set look like? What are these V's? We need the original paper, don't we? M4 competition paper. Actually, I might look up Element AI's GitHub and do they have just the dataset? Oh, datasets, m4.py. What have they done? So this is them loading in the dataset. Okay. Ah. Okay, so this is them. I might just use their function for loading in data. Load. M4 dataset.load. Okay, so they've got a pretty extensive way to download data here. So if I just copy this, they've got their model code here, right? mbeds.py, but I don't want to look at that yet. I just want to, yeah, there we go. The notebooks directory contains a notebook per experiment with the final score. All right, so they've got some pretty good code here loading the data. But I want to see how it was formatted, data sets. M4.py. How did they format it? They turn it into a... So they just read it like a CSV, like I did. Oh, info file path. Okay, what's the info file path do? This is what we might have missed. Info. Okay, there we go. info equals PD. You know what? I'm just going to get one of these data sets working and then try and build a working model. How about we do that? What's the Billy grind? M4 methods. M4 ID. Oh, info is pretty big, isn't it? Oh, I see. 100,000 rows. Okay. So they get so they set up the training cache file path. Okay, let's go info. I just want one set of data. Okay, so these are all IDs. What does D1 mean? Daily one? I think that would be it. Info, let's index on here. Info, M4 ID, dot contains. Can you do this in pandas? How do you pandas cell contains string? ML coders on Twitch, yeah, of course. George Hotz, Twitch. I love watching George Hotz. There's also Mark Safram. I'm probably saying that wrong. Twitch. Follow. Boom. There's two text ML streamers on Twitch. Okay, so we're formatting data here, all right? Oh, string.contains, that's what we need. We just want one data set that works. That way we can replicate this paper and then... Okay, so I don't know where they're getting... Oh, I'm only seeing the head here, aren't I? My goodness, Daniel, you moron. Okay, so each of these is a data set. Beautiful. Daily. Okay, so I think this is a data set. All right, there we go. Okay, daily. Let's get the head. So each of these is a data set that goes up to some length. Let's get D1. So daily D1 equals daily D1. What does this look like if we transpose it? Excuse me? Oh, no. No, we want just this. So that's lock or iLock? I can never get these around the right way. Okay, there we go. So these are our steps. And then if we D1, we have a look at that. And D1 reset index in place equals true. Is this a series? Can I turn this into a data frame? I'm very rusty with pandas at the moment. Okay, there we go. PD data frame. D1 new. Let's get real hacky, shall we? Reset index in place equals true. What does this look like? D1 new. Oh crap. D1 new. What does this look like? Show me what this looks like. What? Oh, because I've set it to a variable in place. Ah, come on, man. Okay. Reset index. Now we want to D1 new. How to drop a row in pandas. Oh, I can just drop along the first axis, right? There we go. What does this look like? This is very hacky. Very hacky. Oh, I only needed to do that. Okay. I'm refreshing myself on pandas here. Okay, so maybe we can go dot drop 0 dot reset index dot drop index. How's this look? I will promise you we'll get some data in a second. Okay, looking better. D1 new dot plot oh, my bad. This is how rusty I am with pandas. Key error 0. What's this column name? Okay, we have a time series. Hallelujah. Okay, we have a time series. This is exciting. That took far too long, but now let's use this as our data. Text, get data, start with a noob time series. Only one out of the possible 100,000 of M4. So we want to start smaller, right? Now let's clean this up a little. Transpose. Do I need to reset index here actually? What's happening here? So this is days and this is value. There's a pandas one-liner here that should work, and I can't think of it. Reset index. That'll do, who cares? D1 new equals D1 new dot drop. Oh, this is classic Colab issues. No, Jupyter Notebook issues. Okay, there we go. D1 new equals pandas rename column. We're getting a data set ready, people. This should have all been done in one line in pandas, but as you see, my pandas skills are very rusty. Come on, bruh. Did that lie to me? Oh, I think this will do it in place. Okay, wonderful. We have some values, and we go to time series. Great. What happened here? Boom, 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 boom. So it looks like this cuts off at about 1,000. How many? Okay, so this only has 1,000 steps. So we need to keep that in mind. Plot. We have a time series. Okay, now we need some way to, they obviously have some nice code to prepare the data sets, so we'll link this in here. For M4 data, there is a nicer way of doing things here. Don't look yet. We want to build our own model. I need to piss and get some water and I'll be back. Okay, so it's 3:30 now, and it's my friend's birthday dinner at 6, but I want to do a workout before then. So I'm probably going to go till about 5 p.m. my time. We'll see how far we can get, hey? I'm probably going to continue this stream over the next couple of days while I replicate this model. So be sure to do whatever you need to do for Twitch to tell you that I'm live, but let's see how far we can get in the next couple of days, eh? So data sets, all right. So let's write this down. Get data, format data. Want to replicate this, we'll get rid of that. We'll write down this text. Download data. get data from M4 competition. And again, this is already replicated on GitHub. I know, it's in PyTorch. I'm going to do it in TensorFlow because I'm more experienced with TensorFlow. Models. See, this is the folder we're not looking at for 3 days until I replicate it. From M4 competition, format data. Start with newbie 1 time series dataset. Build model. Model is located in here. Paper. Here we go. Model. Okay, let's deconstruct this, hey? Build model, figure 1, here. So we've got a little data set, time series, that took us, well, okay, this is another thing with machine learning, right? Is getting this data is very important because it doesn't matter, we don't have a model if we don't have data. So although I did spend a little bit of time hacking around this to get one simple data set, we could spend the next 3 days, in fact, replicating this this Python script that they used to format their data sets. So this is obviously, someone didn't write this in one sitting. It was done in many different trials and errors of exploring data like this, unless they're a freak. They probably did a fair bit of exploring like this and figured out, okay, the data set's structured like this, and now we can functionize it to look something nice like this using classes and static methods and whatnot. But now we have a data set, so the next step will be to format it. Format data. Time series data. So let's write this down. To format time series data, we want to turn it into a supervised learning problem. So let's actually write down the goal. We have a time series. Goal, build model to use steps from past to predict future. So we want to use, like, say, the first 800 steps to predict the next 200 steps. And some steps that we could do to here is to remove the trend. So you see how this goes up in a linear fashion, so from left to right. So one of the common pre-processing steps in time series data is to remove that trend. So you would make the line go across like this, but the values would still be scaled. So to format time series data, we want to turn it into a supervised learning problem. One common method for doing this is windowing. Now I believe we do have some standardized values for how big the M4 competition windows were. So yeah, if we look here, time horizons. So for the daily data, they wanted us to predict 14 steps. So we could actually see this, not just from the repo, but from the original paper. Where we got here? Info, oh no, it's from the info. So we're working with daily data, and we want to predict 14 days into the future, okay? So we currently have a daily data set. Want to predict 14 days into the future. See, this is what I'm saying, right? With have a README for your data sets. That's the most important part of machine learning. See this little info, M4 ID, daily. So the horizon, the time horizon we're trying to predict is 14 days. See info, data frame above. And what is our predictive window that we're using? Frequencies 1, okay. Horizons map, daily, frequency map, whatever that is. Frequency map. Not sure what this is. Equals 1. This might be... No, I don't actually know. I'm not going to try and guess. But let's just keep going. But let's give an example of windowing. Example of windowing. Let's keep it nice and simple. So window for a week. Say we had values for days. We'll start at 0 because we're using Python. Reppin 5, 6. Well, that's 7 days, isn't it? So we might use the first 6 days to predict number 7, right? And then the next window would be 1, 2, 3, 4, 5, 6, 7. We might use that window to predict 8. And then the value, this is the value for each day, right? We might use the next window subsequently. You're following along here? So all of a sudden, our time series data goes from a humble little line to being a supervised learning data set. So we might use, say, this little section here to predict the next section, this little section here to predict the next section, and so on and so on. This is univariate time series, right? Univariate time series. We're only using one type of variable to predict the next variable. If we wanted to incorporate something else about this data set, which we don't actually have, because all we have is a single line, just like the price of Bitcoin. Again, do not use these models for financial predictions. But yeah, let's see what we can do. How to format this data. Should we format it first? Into a window? Yeah, we need a window. We need a data set, don't we, for it. It won't work with the model. But that's just one example of windowing too, by the way. Like you could try to predict 3 steps at a time. Like this, 7, 8, 9. This is a tunable parameter, by the way. How big your window is tunable. Let's just Wikipedia this. Time series windowing. Where is it? Time series windowing. What's Wikipedia tell us? Too much. Is there a graphic? Time series windowing. What's images tell us? Yeah, again, Google Images is just, oh, this is good. There. This is what we're trying to do. Take that and predict 1 day ahead. And we're going to move our window along. Oh, Uber have this as well. This is a great article that we looked at before. Where is this? Here, sliding window. Does this make sense? What we're doing? 2 major approaches to test forecasting models. So, okay, pop quiz to people watching. Format data. How do we make, this is your quiz, how do we make train test sets for time series? Let's have a look at the data. D1 new, values, plot. Pop quiz. Anyone in the stream can answer this. You've got a minute. I'm going to write a timer here. Timer. How do we make train test sets for time series? Pop quiz for the stream. You got 60 seconds. Jack, how are you, my friend? Good to see you. Mark, thank you for the update on how to say your name, Seraphim. Wow, that's so much easier. Seraphim. Ashik says, so this applies to every time series time problem. Convert it to a supervised and build a model on top of it. This is one approach. There may be more, but this is the one I'm looking into it at the moment. We've got 10 seconds left. Cross-validation. Oh. G Union says 80%. Time's up. Time's up. G Union says 80% train, 10% validation, 10% test. G Union, you're very close. Well, actually, yeah, that's one form of right. But Ashik, cross-validation, you've got to be very careful with using cross-validation for time series. What you have to do is, so imagine cross-validation, right? You're going to, because what's the whole premise of time series? You want to use the past to predict the future. So you have to be very careful when you make your train and test sets for time series. You can't just do them randomly, like in, say, image classification. Because if you do cross-fold validation as well, if you fold, say, this into here, you're going to be using data from the future to predict the past. You're going to be mixing up your data sets. But let's visualize this. So when making splits for time series data, you have to be careful not to get data from the future into the past. Okay? So if this is 1,000 steps right now, and we wanted to predict 800 to 1,000 using here, how could we make that split? So we want to predict 800 to 1,000 using 0 to 800. So we just draw a line here and split that as the training set, and this is the test set, right? So this is what you have to be careful of if you are doing these splits randomly. Let's visualize the randomized split. So let's make a wrong split first. So we'll get scikit-learn's, is it model selection? I'm not sure why it's in train test split, and then we will feed it in. No, we actually need to turn this into arrays, don't we? Yes, we do. So turn data into arrays. So right now our data's in data frame format. So we want values equals df d1 new values dot to numpy. Does that give us values? Yes, but we want to remove the nans. Let's just remove them from d1 new, hey? d1 new drop na. Beautiful. d1 new is na. Okay, we need to do that in place, don't we? So let me give you an example of what I mean. Okay, we got some values, and we also need, how do I just get the indexes? So steps equals, or we'll call this time steps equals d1 new dot. What does time steps look like? Does that just give us? We'll put that as an NP array too. Okay, we're being very hacky at the moment, but that's just because we're just playing around, aren't we? This is how we learn, right? Okay, now let's make the wrong split first. So we've got two arrays, values and time steps. Okay? So if we did train test split, we got x train, y train, x test, y test. Is that the right order for train test split? I can never remember the order. Train test split. Oh, it's x first, then y. X first, then y. X first, then y. Someone remind me to use that song later. So now we're going to create a wrong split for time series, and I'll show you why. It's going to be very... values is our x, yes, and time steps is our y. Test size equals 0.1. Now we'll actually put 20% of the data. All right. Okay, beautiful. Now we'll go plot wrong splits. So import matplotlib as plt. We're spending a lot of time on data formatting, by the way, because that's where you're going to spend a lot of your time anyway. So although the stream says like replicating model and whatnot, we'll do that over the next couple of days. We need to get a data set ready first. PLT, let's get just a simple plot, and we'll get xtrain. No, we'll get figure. Plot.figure. Fig size is going to be my favorite hand in poker. 10.7. 10.7 plot xtrain ytrain label equals training data. Let's just have a look at what this looks like, hey? Plot legend. What can we call the x-axis? X label equals time steps. PLT y label equals values. This is an arbitrary univariate time series. Don't know what it is. Oh my goodness, what did we do wrong here? We need a scatter plot, don't we? How do we make the dots smaller? So there's our line here. Now look what happens. Right, so what's wrong with this plot? When they make those dots smaller. Matplotlib make scatter dots smaller. Scatter S size, so S equals 10. I'm going to even make it smaller. Okay, so what's wrong with this? What can you see that's wrong? Look what happens when we put X test, Y test here. Right. So we see that the time steps, why is that starting from 1,000? I've got my axes mixed up, don't I? So the time steps are, no, that should be correct. What's wrong here? X? No, X is the time steps. And Y is the values. Yeah. At least one array required as input. What's happened here? Oh, it doesn't take parameters. Okay. Oh, that's why our data was looking strange. But look what's happened here. We've got test data scattered throughout the past data. And time series, if we're trying to predict the future using the past, we can't have our test data leaking through all of our training data. So, how would we correctly split this? All I want is a train and test set. I don't want cross-validation, I just want train and test. So you've got another minute to think about this. Timer. How would we fix this split? Go. How do we fix our train test splits? The above is wrong. Test data is leaked all throughout the training data. Right, our goal is to, it helps to keep in mind, goal, use past data to predict future. E.g., use first 800 steps to predict next 200. All right, who's got an answer? Beautiful. So G Union says maybe just the last day of the week as validation. That's one option. But what we're going to do is we're going to build a model that's going to take in the first 800 steps and try to predict the next 200. So let's use it indexing. Let's use indexing. So xtrain equals the split. We'll create a split variable. Split equals len values times 8. What does split give us? 80% split. But we want to int this. Okay, so the split, now we're going to create xtrain, xtest equals values, and values will get up to split for xtrain, and for xtest we'll get values from split onwards. And then ytrain is going to be, ytest is going to be, oh no, x is the time steps, isn't it? Time steps. And then y is going to be up to the split, values, split. And then let's have a look at plot indexed splits. So we'll just copy this. Boom. See what we're trying to do now? Trying to build a model to take in this, to predict this. So I'm going to also write in here some to-dos. Does that make sense? To do more data formatting options. We could do seasonality removal, trend removal. I'll look into those later. Now we need to turn data into windows. So our job's not finished yet. Before we decided we want to use a supervised learning type setup. So that's what we're going to do here. We need to turn our data into windows. TensorFlow has a great TensorFlow windowing. Boom. Window. This is what we want for turning our data into windows. We can use TensorFlow's tf.data dataset package. Okay, so see what's going on here. Let's just bring in TensorFlow. And let's just copy this simple example that they use, TF data. We will eventually clean this code up, but for now, we're hacking. We want to print list window dot as numpy iterator. See what happens there? Let's have a look at, let's just have a look at what would happen if we created tf data.dataset.range 7. Is this going to have a numpy iterator method? I don't think so. So this turns window turns an array into windowed data sets. So this is where we can start to get towards turning our data into a supervised learning problem. So we need to build something like this that's going to turn this into a windowed data set. So if we go, where are we at? Let's just get rid of all these useless tabs. Could we write some code to do that? See what I mean? Here's what we want. We want to turn this into something like this. See, we got training, forecasting, training, forecasting. So let's, but we don't know what the size of our windows is going to be. This will make more sense once we've actually done it. So let's go here, TensorFlow time series forecasting. I believe they will have some sort of functionality that we can. Window, split the data. Wonder if we can write the hacky version first and then we'll upgrade it to TensorFlow. Make hacky version first. Data equals empty list, labels equals empty list, for value in values. Now we need a way to store, so this is going to be iterating through values. We could do a list of lists. How would we do this? Let's write it in English first. So step through values, store X values in a window. X equals window size. Make labels of Y of Y. Store X plus 1, X plus Y values in labels. Y equals number of steps to look ahead. Step through values and finish with X and Y pairs where X is a window of certain number of steps, Y is a few steps ahead of X. Actually sounds quite straightforward. But can we do it iterating at the same time? We're going to have loops and loops, aren't we? Let's define window size. As I said, we'll do the really hacky window item in window size. Current window and current labels. This is going to make it too large of a window size, isn't it? Oh, let's write it out first, shall we? Window item in window size, current window dot append value. And then we want, what does current window look like? How is this invalid syntax? Someone, am I missing something? Oh. Okay, so this is going to replace Thank you. Thank you very much. G-Union, I missed that. Okay, so now we're getting a list. Data. See you, Mark. Thank you for tuning in, my friend. I'll see you next time. Enjoy your night. All right, this is a lesson in recursion of what not to do. So as you can see, our current list is only using the most recent value. So we've got value is being appended to current window, and then we need, no, if we're creating current window here, and then looping here, no, this is not going to work. I need to think through this. So step through an array of values while storing the most recent 10, then appending those recent 10 to an overarching list. So for every 10 values, yes. Oh, I just had it in my head. I just had it in my head. Yes. We'll count the values here. We'll get an enum, enumerate. Let's see if this works. Enumerate values, and then if I am 10 equals 0, do something. Yes, this is what we want. Current window. Again, I said we'll do the hacky version first. We can clean this up. We're building a sliding window function from scratch. Sliding window function from scratch. There are already implemented versions of this in TensorFlow. I just want to understand how this is made. Okay, so we get rid of this. Every time we want to append to the current window, we append value. But if we've got 10 values in our window, if I divided by window size equals 10, we want to then data.append current window. What does this look like? Oh my goodness. Ah, no, because our list will get overridden every iteration. Alaichai, how are you? Alaichi? This is not going to work, is it? Can we do this with indexing? there's a way to do this. Values, no. NumPy array, index, here's what we want. So index, start, stop, okay. SK Time had a great guide on this. SK Time. SK Time, they have a class to do this, but I want to do it from scratch. And there's a smart way to do it, but I can't think of it at the moment. Here we go. Yes. Okay, so they use some great NumPy methods here. Let's just reproduce this function, hey? Xtrain, we need to so let's step by step through this function. We'll do just Xtrain first. Okay, so they're reshaping it to that. Oh, I see. And then we want to roll it. What does this look like? M. MP roll. What's the doc string for MP roll? Oh, it's important that we have our data. Okay, so no, this is not going to relate to us. This is beautiful. So right now, our Y train is we actually want Y train MP roll train This is not going to work, is it? Oh, I'm getting a bit lost at the moment. Taurus, I'm using... Oh, here we go. Did that do anything? Yes, it did. Not. Where do they use Y? This is not the M1 MacBook. This is my MacBook Pro. Intel i9. Alright, so we've got half an hour. I want to get a data set ready. So I'm going to use TensorFlow. Data set equals values. Window. That's what we need. There we go. We've got windows of size 10 here. But now we need labels. See you, Sheik. Thank you for coming along. What do you mean, Taurus Johnson, by navigating through code so fast? Do you mean like this? I jump around. But now we need to create this we need to make labels here. I'm just holding command and pushing the arrows. Oh, that just changed tabs. So let's how are they generating windows? window size, shift. I have a notebook here that I was working on this before. Oh, this is the same notebook. So if let's look up flat map. What are the default values for window? Now, if we don't have shift equals 1, yeah, so that's what shift equals 1 does, is it moves our data. Yeah, we want shift equals 1. So now we have windows so see how this one goes from 1017 to 1019 and finishes on 10215. This next window shifts over 1019.3, starts from here and then goes there, and then it's got one extra value. So all it's doing is it's shifting over one step at a time. And now we want to what happens if we flat map it? Dataset.flatmap. Lambda window. what's happened here. Okay, so now all of these are tensors. Now we need to create the labels. We want up to the last one. And including the last one. Oops. What have we done wrong? There. Boom. Now we have tuples of windows and labels. So we want to use these values to predict this value. And then these values to predict this value. This value to predict this value, and so on. Now we can batch it up. Prefetch. Okay. So we've got a data set now. Let's now build a simple model. getting very dark in this room. Inputs equals what type of model should we build? Column 1D. See how our model goes, hey? Oops. What did we do wrong? Use a default window size of 10. Where is this error coming from? Shapes are tensor 8 batch 9. Derp. Might not need this. Booyah! Okay, our model's not learning anything though. Let's just stack some more layers in here. Okay, still just as good as random guessing. Or maybe we want linear here. There we go. Okay, activation function was wrong. We had a sigmoid on the end there, not linear. Okay. So now let's plot some predictions. This is going to have to be what shape is this? Yo, Renuga, what's good? So I need to get my data in the right input shape. I wonder if this changes. So I think this has got something to do with the kernel size. Yeah, okay. So my kernel size is affecting what's happening here. What if I expanded the dimensions twice? Now we might be cooking with gas. No plans on a PyTorch course anytime soon. PyTorch versus TensorFlow for reinforcement learning. I think you'll probably find PyTorch has more options in that. I don't get this. Am I using Conv2D? No. It is 5 p.m. Oh, that means it's time for me to go. Yeah, I'll probably stream tomorrow. Okay, so our prediction is broken. Still live, man. I'm about to bounce though. So, today's stream we talked a lot about different time series methods, etc., things you have to keep in mind. We're going to continue on this later on. I'm just going to get out of all the extra stuff that we don't need. But we're going to keep working towards re-implementing this paper. So, we've got a simple model up and running. It's working okay, but our predictions aren't really working, so we need to evaluate it in some way. So model predictions are broken. We need to get data inflow and outflow correct. So we'll do that first. Once data inflow, outflow is correct for a sample series, replicate model in paper. So that's our important next step, is to make sure our data loaders and data predictions work. Can we format? But yeah, I'll be back tomorrow at some point and we'll continue off where we left off. So, thank you for tuning in. I've got to go do a quick workout before I go to a friend's birthday party. If you want the code, let me know. We could probably work on getting this up in a GitHub tomorrow or something like that, but it'll eventually be part of this module on the TensorFlow course. But yeah, thank you all for tuning in. Have a great evening, morning, day, wherever you are in the world, and keep machine learning. Peace.